Hello student, welcome to the lecture on game theory and decision making, and after this lecture we will be able to learn the following objectives. Give details of the game theory and information systems. Talk about the types of game theory. Describe the two-person zero-sum games. Recognize the decision under uncertainty. Hello students. Today we will discuss game theory and decision making. Let's start with the history and impact of game theory. Game theory is the formal study of conflict and cooperation. Game theoretic concepts apply whenever the actions of several agents are interdependent. These agents may be individuals, groups, firms, or any combination of these. The concepts of game theory provide a language to formulate structure, analyze, and understand strategic scenarios. In 1950, John Nash demonstrated that finite games have always had an equilibrium point at which all players choose actions which are best for them given their opponent's choices. This central concept of non-cooperative game theory has been a focal point of analysis since then. In the 1950s and 1960s, game theory was broadened theoretically and applied to problems of wars and politics. Since the 1970s, it has driven a revolution in economic theory. Additionally, it has found applications in sociology and psychology and established links with evolution and biology. At the end of the 1990s, a high payroll application of game theory has been the design of auctions. Prominent game theorists have been involved in the design of auctions for allocating rights to the use of bands of the electromagnetic spectrum to the mobile telecommunications industry. Most of these auctions were designed with the goal of allocating these resources more effectively than traditional governmental practices and additionally raised billions of dollars in the United States and Europe. Now we will talk about the game theory and information systems. In game theory, a game is a formal model of an interactive situation. It typically involves several players. A game with only one player is usually called a decision problem. The formal definition lays out the players, their preferences, their information, the strategic actions available to them, and how these influence the outcome. The nature of competitions against other human beings means that there are a limited number of options, some of which are more profitable than others. The purpose of studying a game is to determine which option your opponent will choose and select the option that best reacts to this and puts you at the advantage. The central purpose of game theory is to study the strategic relations between supposedly rational players. Game theory allows us to another. This will allow us to think on our feet much better and make better decisions on certain situations. Game theoretic concepts apply whenever the actions of several agents are interdependent. These agents are interdependent. These agents may be individuals, groups, firms, or any combination of these. The concepts of game theory provide a language to formulate structure, analyze, and understand strategic scenarios. The internal consistency and mathematical foundations of game theory make it a prime tool for modeling and designing automated decision-making processes in interactive environments. For example, one might like to have efficient bidding rules for an auction website or tamper-proof automated negotiations for purchasing communication bandwidth. The process of formally modeling a situation as a game requires the decision maker to enumerate explicitly the players and their strategic options and to consider their preferences and reactions. The discipline involved in constructing such a model already has the potential of providing the decision maker with a clearer and broader view of the situation. This is a prescriptive application of game theory with the goal of improved strategic decision making. Game theory and information systems. So after discussing game theory and information system with the history and impact of game theory, now we will move on to differential games. Differential games such as the continuous pursuit and evasion game are continuous games where the evolution of the player's state variables is governed by differential equations. The problem of finding an optimal strategy in a differential game is closely related to the optimal control theory. A particular case of differential games are the games with random time horizon. In such games, the terminal time is a random variable with a given probability distribution function. Therefore, the players maximize the mathematical expectancy of the cost function. It was shown that the modified optimization problem can be reformulated as a discounted differential game over an infinite time interval. Cooperative or non-cooperative. Cooperative game theory. It is simply coalitions of players. Like in politics, they join forces to make a law. Because they have only one agenda, but it has competition involved also because you will encounter a rival group or opposing group. The difference of non-cooperative game theory. Two or more individuals within the same environment with different goals. Without sharing their ideas, they can make a decision. A game is cooperative if the players are able to form binding commitments. For instance, the legal system requires them to adhere to their promises. In non-cooperative games, this is not possible. And non-cooperative, often it is assumed that communication among players is allowed in cooperative games, but not in non-cooperative ones. Hybrid games contain cooperative elements. For instance, coalitions of players are formed in a cooperative game, but these play in a non-cooperative fashion. Simultaneous and sequential. The difference of simultaneous to sequential theory. There's no time involved here and you're doing actions that you do not think your move first, like rock, paper, scissors, because you both make randomly decisions. It is represented by normal form or payoff matrices. It is also called strategic game. Sequential game theory is a kind of game theory you need to know the consequences before you can make a move. This kind of game involves time like chess, backgammon. Sequential is represented by decision tree or extensive form. It is also called extensive game. Simultaneous games are games where both players move simultaneously, or if they do not move simultaneously, the later players are unaware of the earlier players' actions, making them effectively simultaneous. Sequential games or dynamic games are games which later players have some knowledge about earlier actions. This need not be perfect information about every action of earlier players. It might be very little knowledge. For instance, a player may know that an earlier player did not perform one particular action, while he does not know which of the other available actions the first player actually performed. Metagames. In simple terms, it is the use of out-of-game information or resources to affect one's in-game decisions. The games which are played for the development of the rules for another game, the target or subject game. Meta games seek to maximize the utility value of the rule set developed. The theory of meta games is related to mechanism design theory. The term meta game analysis is also used to refer to a practical approach developed by Nigel Howard, whereby a situation is framed as a strategic game in which stakeholders try to realize their objectives by means of the options available to them. Subsequent developments have led to the formulation of confrontation analysis, perfect information and imperfect information. A game is one of perfect information if all players know the moves previously made by all other players. One popular game for perfect information is chess. Imperfect information is simply the opposite. Players do not know the moves made by the other players, thus limiting their information to strategize. Some examples are poker and battleship. An important subset of sequential games consists of games of perfect information. A game is one of perfect information if all players know the moves previously made by all other players. Thus, only sequential games can be games of perfect information, since in simultaneous games, not every player knows the action of the other. Most games studied in game theory are imperfect information games, although there are some interesting examples of perfect information games, including the ultimatum game and the centipede game. Perfect information is often confused with complete information, which is a similar concept. Complete information requires that every player knows the strategies and payoffs available to the other players, but not necessarily the actions taken. Games of incomplete information can be reduced, however, to games of imperfect information by introducing moves by nature. Infinitely long games. Real-world games consist of a finite number of moves, but mathematicians and theorists said there are infinite moves that is unknown until all the other moves are completed. Games as studied by economists and real-world game players are generally finished infinitely many moves. Pure mathematicians are not so constrained, and set theorists in particular study games that last for infinitely many moves with the winner or other payoff not known until after all those moves are completed. The focus of attention is usually not so much on what is the best way to play such a game, but simply on whether one or the other player has a winning strategy. It can be proven using the axiom of choice that there are games even with perfect information and where the only outcomes are win or lose, for which neither player has a winning strategy. The existence of such strategies for cleverly designed games has important consequences in descriptive set theory. Combinatorial games. The study of sequential games with perfect information, that is, two-player games which have a position in which the players take turns changing in defined ways or moves to achieve a defined winning condition. Games in which the difficulty of finding an optimal strategy stems from the multiplicity of possible moves are called combinatorial games. There is no unified theory addressing combinatorial elements in games. There are, however, mathematical tools that can solve particular problems and answer some general questions. Games of perfect information have been studied in combinatorial game theory, which has developed novel representations. Example, surreal numbers as well as combinatorial and algebraic and sometimes non-constructive proof methods to solve games of certain types, including some loopy games that may result in infinitely long sequences of moves. Symmetric and asymmetric. A symmetric game is a game where the payoffs for playing a particular strategy depend only on the other strategies employed. One well-known game for this example is the prisoner's dilemma. On the other hand, asymmetric games are games where the strategies of both players are not identical. A symmetric game is a game where the payoffs for playing a particular strategy depend only on the other strategies employed, not on who is playing them. If the identities of the players can be changed without changing the payoff to the strategies, then a game is symmetric. Many of the commonly studied 2x2 games are symmetric. Most commonly studied asymmetrical games are games where there are not identical strategy sets for both players. For instance, the ultimatum game and similarly the dictator game have different strategies for each player. It is possible, however, for a game to have identical strategies for both players yet be asymmetric. For example, the game pictured to the right is asymmetric despite having identical strategy sets for both players. Two-person zero-sum games. Each player's expected utility in Nash equilibrium must be equal to 0. Imagine it is not the case, then the winner earns a positive amount and the loser earns a negative amount. But the loser could always copy the winner's strategy and earn 0, which is a profitable deviation. Now suppose that the second DM is a clever opponent that makes decisions in the same way that the robot would. This leads to a symmetric situation in which two decision makers simultaneously make a decision without knowing how the other will act. It is assumed in this the DMs have diametrically opposing interests. They are two players engaged in a game in which a loss for one player is a gain for the other and vice versa. This results in the most basic form of game theory, which is referred to as a zero-sum game. Game formulation. Suppose there are two players, 1P and 2P, that each have to make a decision. Each has a finite set of actions U and V respectively. The set V can be viewed as the replacement of from formulation by a set of actions chosen by a true opponent. Each player has a cost function I is equal to 1, 2. An important constraint for zero-sum games is L1 UV is equal to L2 UV, which means that a cost for one player is a reward for the other. This is the basis of the term zero sums, which means that the two costs can be added to obtain 0. In zero-sum games, the interests of the players are completely opposed. In light of 1, it is pointless to represent two cost functions. Instead, the superscript will be dropped and L will refer to the cost L1 to P1. The goal of P1 is to minimize L. Due to 1, the goal of P2 is to maximize L. Thus, L can be considered as a reward for P2, but a cost for P1. A formulation can now be given. Formulation A zero-sum game, two players P1 and P2. A non-empty finite set U called the action space for P1. For convenience in describing examples, assume that U is a set of consecutive integers from 1 to mod U. Each U element U is referred to as an action of Pi, as an action of P1. A non-empty finite set V called the action space for P2. Assume that V is a set of consecutive integers from 1 to mod V. Each V element V is referred to as an action of P1. A function L ratio U xV implies U is called the cost function for P1. This also serves as a reward function for P2 because of 1. Deterministic strategies. What constitutes a good solution to formulation? Consider the game from the perspective of P1. It seems reasonable to apply worst-case analysis when trying to account for the action that will be taken by P1. This results in a choice that is equivalent to assuming that P2 is nature acting under the non-deterministic model. For a matrix game, this is computed by first determining the maximum cost over each row. Selecting the action that produces the minimum among these represents the lowest cost that P1 can guarantee for it. Let this selection be referred to as a security strategy for P1. Randomized strategies. The fact that some zero-sum games do not have a saddle point is disappointing because regret is unavoidable in these cases. Suppose we slightly change the rules. Assume that the same game is repeatedly played by 1P and 2P over numerous trials. If they use a deterministic strategy, they will choose the same actions every time, resulting in the same costs. They may instead switch between alternative security strategies which cause fluctuations in the costs. What happens if they each implement a randomized strategy? In the limit, as the number of times the game is played tends to infinity, an expected cost is obtained. One of the most famous results in game theory is that on the space of randomized strategies, a saddle point always exists for any zero-sum matrix game. However, expected costs must be used. Thus, if randomization is used, there will be no regrets. In an individual trial, regret may be possible. However, as the costs are averaged over all trials, both players will be satisfied. Decision under uncertainty. The phrase decision under uncertainty refers to the problem of taking decisions when we do not have a full knowledge neither of the situation nor of the consequences of the decision, as well as when the consequences of decision are non-deterministic. For example, a manufacturer of laptops is faced with the problem of selecting one of the two models to be manufactured. The profit depends on the market acceptability of the model, which at present is uncertain because it has been broadly classified into 4 categories: excellent, good, fair, and poor. The profit or losses expected by the management from the different levels of market acceptability of the models is given in the table format. Paradoxes of uncertainty. The distinction between uncertainty and probability has centered on 2 paradoxes. One of them is the paradox of ideal evidence. Measures of incompletely known probabilities. This rule that have been proposed for decision making under the uncertainty, partial probability information all make use of some quantitative expression of partial probability information. Measures of uncertainty will be introduced. There are 2 major types of measures of incompletely known probabilities. A binary measure divides the probability values into 2 groups, possible and impossible values. In many cases, the set of possible probability values will form a single interval, such as the probability of a major earthquake in this area within the next 20 years is between 5% and 20%. Multi-valued measures generally take the form of a function that assigns a numerical value to each probability value between 0 and 1. This value represents the degree of reliability or plausibility of each particular probability value. Second, order probability. The reliability measure may be seen as a measure of the probability that the true probability has a certain value. Decision criteria for uncertainty. Several decision criteria have been proposed for decision making under uncertainty. 5 of them will be presented here. Maximum expected utility. According to the maxim in EU expected utility rule, we should choose the alternative such that it is lowest possible EU, that is, lowest according to any possible probability distribution is as high as possible. Maximize the minimal EU. For each alternative under consideration, a set of expected values can be calculated that corresponds to the set of possible probability distributions assigned by the binary measure. The lowest utility level that is assigned to an alternative by any of the possible probability distributions is called the minimal expected utility of that option. The alternative with the largest minimal expected utility should be chosen. This decision rule has been called maximum expected utility MMEU. It is an extremely prudent or pessimistic decision criterion. Reliability weighted expected utility. If a multi-valued decision measure is available, it is possible to calculate the weighted average of probabilities, giving to each probability the weight assigned by its degree of reliability. This weighted average can be used to calculate a definite expected value for each alternative. In other words, the reliability weighted probability is used in the same way as a probability value is used in decision making under risk. This decision rule may be called reliability weighted expected utility. Ellsberg's index, the use of an optimism-pessimism index to combine maximum expected utility with what is essentially reliability weighted expected utility. He assumed that there is both a set YO of possible probability distributions and a single probability distribution Y0 that represents the best probability estimate, modified MMEU. Decision rule that makes use of a measure ρ of epistemic reliability over the set of probabilities and certain minimum level ρ0 of epistemic reliability is chosen. Probability distributions with reliability lower than ρ0 are excluded from consideration as not being serious possibilities. Levy's lexicographical test. It is assumed that we have a permissible set of probability distributions and a permissible set of utility functions. Given these, he proposes a series of 3 lexicographically ordered tests for decision making under uncertainty. They may be seen as 3 successive filters. Only the options that pass through the first test will be submitted to the second test, and only those that have passed through the second test will be submitted to the third. First test is E-admissibility. An option is E-admissible if and only if there is some permissible probability distribution and some permissible utility function such that they in combination make this option the best among all available options. Second test is P-admissibility. An option is P-admissible if and only if it is E-admissible, and it is also best with respect to the preservation of E-admissible options. Third test is S-admissibility. For an option to be S-admissible, it must both be P-admissible and security optimal among the P-admissible alternatives with respect to some permissible utility function. Security optimality corresponds roughly to the MMEU rule. Summary. A set of potential states is given representing the circumstances about which there is uncertainty. It is logically necessary that one and only one of the states will occur. Otherwise, the states have been erroneously specified. The decision maker is able to assign to each potential state a precise probability. The expected value of an alternative course of action is the sum of all possible values of outcomes from that action multiplied by their respective probabilities. In many real-world situations, it is common for the decision maker to have some idea about the probabilities of occurrence of the different outcomes or states of nature.